Hi everybody. Okay, here we are ready to start the second semester of physical science. And remember first semester we talked about physics for the most part once we really got past all the introduction. And this chapter is going to be kind of the segue to go from physics into chemistry, which is what we'll cover for most of the second semester. So this is thermodynamics is the title of the chapter, which essentially means heat change. And so we're going to talk some about obviously about heat, temperature, as it relates to energy, which we've already done a chapter on. But basically, there are lots of relationships between, the physics part of energy and temperature and molecules moving and all that kind of stuff, and chemistry and how those molecules react, states of matter, all those kinds of things. So we're kind of segueing into chemistry through this. So in this chapter, we'll do a little introduction before we start on these notes in class. In the introduction, it will be just like it has been, some of the men and women, I think men in this chapter, who did different experiments, figured out some things about heat in this case. Of course, now I can't think of any of their names off the top of my head. James Prescott Joule, who we've already talked about, Robert Mayer, Benjamin Thompson, who was also known as Count Rumford, all different people who experimented with heat. And so we are actually starting now today, though, just talking about temperature. So temperature is a measure of the kinetic energy of an object's atoms, its molecules, basically how much they are moving. Kinetic energy, remember, has to do with movement. And of course, when we talk about the air temperature, we're talking about the movement of the air particles. And so that's what we're really basing it on the movement. And we measure it in degrees, degrees Celsius, degrees Fahrenheit, Kelvin, this last little unit that is listed here. Typically you just say, 273 Kelvin, you don't say degrees, but that's a different story there. Anyway, we measure temperature using a thermometer, and thermometers basically work by using a substance that expands or contracts at a predictable way as the temperature changes. Most thermometers have to use direct contact, so they actually have to touch whatever the substance is that they are measuring the temperature of. So, it's like if you're having your temperature taken, they will touch your forehead. I know right now in the age of COVID and all that kind of stuff, they're using touchless thermometers, but they put it as close to their head or your head as they can. It's not as accurate when they do it that way, but so anyway, so that is temperature. Okay, so now talking about thermometers and measuring temperature, Galileo, remember he did a lot of stuff. If you're looking for somebody and you don't really know who did something, Galileo probably has something to do with it. But he built the first thermometer and he actually called it a thermoscope. And I have a picture of one there on the screen. And it's basically just a very long glass tube. It has a closed bulb at one end. That's what this little thing is up here. And the other end is down in a flask of water. And as the air in this tube, because it is touching, it is exposed to the air through that bulb, as it heats up, it will expand and push the water down, farther down into the tube. Or as it cools, it will contract, and basically the water level in that long tube changes. And so they use that to tell what is it warmer or cooler than, than it was yesterday or whatever it was. Not that accurate, if you don't have like markings on the tube, and you have to have, very consistent measurements. But first thermometer. Okay, so now temperature scales. So once people started figuring out how to measure temperature and they made, a thermoscope like Galileo did, they're like, how can we make sure that everybody's like using the same scale? and they decided to set some standards, and they would use these standards to calibrate their thermometers. And these were called fiducial points. You may have talked about that when you guys did weather back in 8th grade. But anyway, so these fiducial points are the standards. Typically, one of those points will be the boiling point of water. Water is always going to boil at 100 degrees Celsius or 212 degrees Fahrenheit. And so so that everybody's kind of starting from the same point. Okay, first scale is the Fahrenheit scale, and this was proposed by Daniel Gabriel Fahrenheit. And his original fiducial points were the freezing point of a salt, water, and ice mix, which like you do this when you make like homemade ice cream. You mix the ice with some rock salt, you put a little water in there, and it lowers the temperature. That's why it helps your ice cream freeze. So he used this as like the cold point, and then he used the temperature of the blood of a healthy man, which sounds really weird to me, for the warm point. He realized at some point in there that was a little hard to do. You know, how much salt and how much water, how much ice are you mixing? You know, who's to say what the temperature of a healthy person is? Is it always 98.6? You know, so he eventually changed and decided to use the boiling points of water and the freezing point of water as his 2 points. So he set the freezing point at 32 degrees and the boiling point at 212 degrees. And he actually made a little more usable thermometer than the thermoscope that Galileo had come up with, and it's actually very similar to what we use today. Okay, so that's the first guy. Then we have Anders Celsius. Isn't he lovely? This picture makes me laugh because of how pink his lips are, but who am I to say? Anyway, he used a decimal temperature scale, which means everything is kind of the powers of 10, which is very useful math-wise. And it is part of the metric system. It is the metric measurement of temperature. Most countries, everything's in Celsius. Remember, Americans, we're stubborn and we're hanging on to Fahrenheit. But Celsius is actually easier to use because of the tens, and also because of the fiducial or the standards that he used. He kind of did it weird because he originally placed the boiling point of water at 0 degrees and the freezing point at 100 degrees, which I don't know why he did that, but after he died, they switched it and said 0 is freezing, 100 is boiling. And then everything's kind of the powers of 10, and it is a little bit different scale obviously than Fahrenheit. You have a bigger gap with Fahrenheit between boiling and freezing, so the degrees are larger. There are conversions obviously that you can do between Celsius and Fahrenheit. Scientifically, we will always use Celsius degrees, and so I don't really need you to know how to convert it. You have an app on your phone, I'm sure, that can do that. So anyway, so that's the second and more useful scale in terms of science. And then the third one is the Kelvin scale. This is a guy, this is Lord William Kelvin, thank you very much. He did not base his on anything besides movement, and he said that if you have the temperature of a gas, you are measuring the movement of that gas. Is very similar to the kinetic molecular theory, and so he based his thermometer, or not his thermometer, he doesn't have a thermometer, he based his temperature scale on the idea of absolute 0, and this is the point where all particles stop moving. This is an unattainable temperature so far. We've gotten very, very close, but it at absolute 0 in the Celsius scale is negative 273.15 something 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 something. Very, very cold, obviously. We have not achieved that point yet, but that is what his scale is based on. There's not a thermometer that you can go buy at Lowe's or anything like that measures Kelvin, but it is probably a more true representation of temperature because it is measuring the movement. Now, typically, and we'll talk about some problems as we go through, but But if you'll remember back when we talked about the gas laws, I know it was before Christmas, but the gas laws during chapter 8, we talked about Kelvin temperatures. And I just gave them to you. But just so you know, to convert from, if you have the Celsius temperature and you want to go to Kelvin, it's very simple. You just add 273. If you have Kelvin and you want to go back to Celsius, you subtract. So just kind of keep that in mind. That was Lord Kelvin's contribution. Okay, so now we've got temperature. And what does change in temperature do to matter? And it can affect properties. It kind of depends on the matter, but there are three main ones to know about. First off is thermal expansion. Many materials expand as they get hotter. So as the temperature goes up, things like metals, concrete, wires, they tend to expand. And you see this in different building materials where there are where they leave gaps, where they kind of take into account this expansion on bridges where they have like the big concrete slabs laid out. If you get out, which I don't recommend obviously getting out of your car on a bridge, but there's usually a gap between those big concrete blocks so that as they get warmer during the summer or as cars drive over and friction, all that kind of stuff, there's a little bit of space for them to expand. I believe it's why they have like the cracks in the sidewalk, same thing, where they have just some space for expansion. You may notice it on really hot days if you're ever, driving out in the country. If there are still, telephone wires, the telephone poles with the wires between them, it's really hot, the wires will start to sag a little bit lower as they get too warm. So thermal expansion. The next one, electrical resistance. So this is only in metals. As temperatures get higher, the electrons that are flowing through a metal, which is a conductor, tend to start to flow randomly, and then the electricity can't flow through in a straight line. It's why, like on your Xbox or your PlayStation or whatever, after you've been playing for a little bit, you hear the fan kick on. Excuse me, because it's trying to cool down the insides of that machine so that the electricity can flow pretty smoothly. But it'll shut down if you get too hot for this reason. Then last one, viscosity. Viscosity is defined as the resistance to flow. That's kind of like the thickness of a liquid. And so this is with liquids. As something gets warmer, it tends to flow faster because the particles move apart a little more. So you can think of like trying to pour like cold syrup, not frozen, but really cold syrup versus warm syrup. Warm syrup, if it's warm enough, it's like pours like water. But if it's pretty cold, it's very slow. So that's viscosity. Okay, now heat. Heat is defined as the flow of thermal energy from one place to another. And it flows or moves in three different ways. And the first one is conduction. This is the movement of thermal energy or heat from one object to another through contact. So this is like if you make the mistake of putting something on the stove and then stirring it with a metal spoon, at first it's not gonna, your spoon's gonna be fine, but if you leave it in the pot as you stir, it's gonna get hotter and hotter. The spoon will get hot. That's because the spoon is touching the hot liquid and then it is moving up the spoon to where your hand is and it gets too hot. And so this transfer, you will have the object with more thermal energy losing energy and feeling cooler as that energy is transferred. The object with less energy feels warmer as energy comes into it. Typically, like in class, I a lot of times say, okay, like think about putting your hand on the table. Remember, are the black tabletops that we have in here that feel so cold? If you put your hand on there for, a length of time and then take your hand off and touch your face, your hand feels really cold. It's because the heat has flowed into the table, leaving your hand feeling cooler. Now, if you leave an object there long enough, the transfer will continue until the thermal energy is the same, and that's thermal equilibrium. And so remember that equilibrium just means the same. You don't always reach a thermal equilibrium because heat can be lost to the surroundings. Just, like we've talked about before with energy, heat heat is hard to hold on to sometimes, and so that always is a little thing to kind of to take into account. Okay, now just real quick, a little side note: conductors. When solids are using conduction, to transfer thermal energy, it is through the vibrations of the particles. So the warm object has particles that are moving very, very fast. As they come in contact with a cooler particle, they're moving really fast, and they kind of bump into this other one and make it move. And so eventually they both end up vibrating at the same rate, and that means they have the same temperature. Good conductors are things like diamonds. Who knew? Metals, of course, silver being the best out of the metals. Copper, aluminum are good. But anything can conduct thermal energy, just some are better than others. Okay, now second way that heat is transferred is convection. And this is when thermal energy is transferred from one location to another by a fluid. Remember, fluids are liquids or gases. And again, it has to do with the vibration, the moving of the particles. And with fluids and gases, you have a random vibration. And so so this helps them kind of spread out. And so with convection, we see this naturally. It's caused by gravity. Warm fluids will rise and cooler fluids will sink because of the differences in density. So this is the whole hot air rises and cool air sinks. And so you have this kind of circle that is formed almost, rising, sinking, and that's natural convection. And then you have convection currents, and we see this in the atmosphere. We see this in bodies of water. Just the rise and fall of the fluids warm up and cool down. Then we have figured out forced convection, and where we use fans or pumps, some kind of duct system to move fluids. Remember, air is a gas, through heating and cooling systems. And then, of course, atmospheric convection, which I kind of mentioned with the convection currents. This is what causes wind, helps regulate temperatures, helps, move air masses from one place to another. So, yeah, second transfer. Okay, radiation is thermal energy transfer through radiant energy. Remember, radiant energy is something that comes from a source and can move through space, can move through a vacuum. The sun is our source of radiant energy, or kind of the best example. And so that energy moves through space, a vacuum, gets to our atmosphere, and then that energy, the movement of those particles, or the energy in those particles, causes the air molecules to start to vibrate faster, and then increase their thermal energy, increase the temperature. So remember, one big difference, one thing to note: thermal energy cannot move through a vacuum. It has to have air or a liquid or a solid, something to carry it. Radiant energy does move through a vacuum. Radiant energy can also transfer thermal energy between objects that aren't in contact. And so, like heat lamps, they heat up the air right around them, and then it moves through the air. So, three ways: conduction, convection, radiation. Don't forget them. Okay, now insulators, we've already talked about conductors a couple pages back. Insulators resist the flow of energy, and they typically have one of two structures, very loosely connected, open structures, like styrofoam, or they have very tightly connected atoms with the electrons that are held very, very close together, and so they just basically resist the movement. The particles just don't pass on the vibrations. Gases are very good insulators because they have widely spread atoms. Just means the energy or the vibration is hard to pass on if you're not in contact. You see this in like the double paned windows that you might have in your house, if you even know about that. But there's basically two panes of glass with sometimes just air between them that helps to keep out the cold and keep in the heat, or vice versa during the summer. Vacuums are very good insulators because there are no particles. So like, the bottles now that you have, like the Yeti cups, they are vacuum between the inner and outer layer, so it helps keep your drink cool or warm. Okay, so now measuring heat in when you have thermal energy changes. So we're looking at a change in temperature, basically. If we're absorbing thermal energy, things are getting warmer, and that the change in the temperature depends on the material, what is actually absorbing the heat and how it is affected. Metals will have a very large temperature change with a small amount of thermal energy. They are very good conductors, we've already said, but they tend to absorb heat very well, and you see a big change. Something like styrofoam will have a very small temperature change when exposed to heat, because they just don't, with all the air that's in between the spaces in the styrofoam, they just tend to not absorb a lot of thermal energy. Okay, so of course, yay, some math. I know you're excited. Two things that you look at with materials is the heat capacity, and that is how much energy does it need to absorb to change its temperature by 1 degree Celsius. And there's a little formula there, and we'll do an example on the next page, but probably a little more useful, at least I have found or I've seen, is the specific heat capacity. And this is a property that can be used to identify different substances. And it's the amount of thermal energy that must be gained or lost to change the temperature of 1 gram of a substance by 1 degree Celsius. So you deal, if you deal with a lot of different materials, different metals, and you want to know, okay, which one is going to be able to absorb more heat than another, you can look through books and books of listings for specific heat capacities. Or if you have an unknown metal and you go through and test it and you find the specific heat capacity, then you can kind of tell what, you can use those books again and figure out what the metal is. Okay, so here is an example from your book. So you have an 850 gram stainless steel bolt. So there is our mass. And it heats up, blah, 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 from 27 degrees to 107 degrees. How much thermal energy is gained? And then they tell you the specific heat for stainless steel is 0.5. Okay, so they are using kind of a modification of the formula from the page before, and it, if you rearrange it, you can write it out like this: Q equals SP times M times delta T. And so the specific heat is 0.5. We'll do units in class, but I just want you to get the numbers. The mass is 850, and then the temperature change is the difference between 107 and 27, which, if I do my math correctly, is 82. Okay, and then you multiply all of those numbers together, and you're going to get 34,800, and this, we're talking about energy, it's measured in joules. So we'll go over it more in class, but I just kind of wanted to see it wanted you to see it if you're using this video. Okay, last thing. Okay, so now heat and phase changes. So when material warms up or cools down, the temperature changes because the molecules are moving differently, either faster or slower. But during a phase change, when it goes from a solid to a liquid or a liquid to a gas, the temperature does not change, because the thermal energy that is being absorbed is actually being used to break the bonds between the molecules, and not to raise the temperature. So there's still heat going in, but now instead of making the molecules move faster, it's actually breaking them apart. And so the heat goes into the breaking instead of to the movement. And there are two different phase changes. You have the latent heat of fusion. This is how much energy is moving or being absorbed or lost when something is either melting or freezing. And then you have what's called the latent heat of vaporization. Same thing, the amount of energy that is being absorbed or lost during something turning to a gas through vaporization, or for a gas condensing back into a liquid. Whew, okay, so I know fast and quick, going through all of this stuff. Obviously in class we'll talk about it a little bit more in detail on some of these things, but please ask me questions if you've got them. Bye guys.